One is called solothermal and the other called hydrothermal. Okay, solothermal and hydrothermal are two main synthesis method that we are going to discuss today. Um, there are the difference between hydrothermal and solothermal synthesis is that um both of them are done in a high temperature. Why we need to increase the temperature? The reason is that we need to um, decrease the delta G of system, because if the delta G of system is high, then you have a high chance that you produce junks, not nanoparticles. Okay. So if you want to have the nanoparticles, you need to keep your system close to equilibrium. So that's why you need to make the G of the system close to equilibrium. And this system, the system I wanted to talk about, is the nanoparticle synthesis will happen in the water. So if the advantages with the water is that, first of all, it is cheap. So water is available everywhere. So you can have water everywhere. In Iraq, in Iran, water is cheap solvent. Secondly, you can have the high purity water. Uh, the problem with water is two problems. First of all, water will boil at 100 degrees C. So if you heat up the water, you cannot heat it up too much. If you heat up the water، if you heat up the water، ببین کامل نیومده مهندس. Okay, I'm in the lab, so someone asked me to go. I went. Sorry. Can you hear me?
Yes,
Can
Doctor.
everyone hear
Yes.
me? Okay, sorry.
Yes, Doctor.
So let's continue. The solvent can be water, can be ethanol, can be methanol, can be benzene, can be color benzene, can be toluene, can be many different kind of solvents. But the advantage with water is that it's very cheap. The disadvantage with water is that it is boiling at 100 degrees. And another disadvantage is that this synthesis method is good for the oxide material, not very interesting for the other kind of material. So if you want to have the oxide nanostructures or nanoparticles, water can be interesting material. But if you want to work with the other kind of materials, I'm talking about the sulfite, selenite, or even different kind of nanomaterials. This is not easy to synthesize it in water. So what we can do for synthesis of the nanomaterial is having different ingredients all in water. All your ingredients should dissolve in water. Okay, you need a salt. So your metallic salts should be dissolvable in water. If you don't use salt, you cannot synthesize your material. Your material should be soluble, and your ingredient salts should be soluble in water. Otherwise, you cannot start your synthesis. Then you need to add a little bit of bases, like base material, like base compounds like ammonia, like sodium hydroxide, potassium hydroxide, urea. So all of these things can be used as a basic compounds. Then you form, and also you need to add a, a weak acid. The weak acid can be citric acid, can be acetic acid, can be acetyl acetone, and many other compounds can be used as a weak acid. These acids will form complexes uh, with your uh, oh, will form complexes with your salt ions. Remember that the mm, what I'm describing in this lecture is also considered as a soldier. So this can be considered as a soldier process. Anyway, when you add bases, then and weak acid, then you will have a solution or a not nanoparticulate. It's a salt. Then you will form a salt. Um, a liquid containing metal hydroxide clusters and supermolecules, yeah. Which called salt. Then you need to heat up this salt. If you heat it up, then hydroxide will form to oxide nanoparticle. But as I told you, you cannot dissolve. You cannot heat up water more than 100 degrees. So if you want to heat up water to higher temperatures, what you need to do is using a tool called autoclave. Autoclave will autoclave will help you for increasing the temperature of water without boiling it. The way autoclave is work is exactly the same as the pressure cooker. Actually, it's increase the pressure inside the uh, boiler, so it's avoid boiling or escaping the vapor from your vessel. Usually, autoclaves are made out of steel, so it's a steel jar. But inside, because the steel can react with the chemicals like weak acid, we usually close it, cover the autoclaves with the Teflon liner inside. And Teflon liners is very expensive. You should be careful about it. So after we get our Teflon liner inside, and we close autoclave, we can heat it up more than 100 degree, and there will be no vapor out. So it won't the water do not escape. So the water will stay in the capsule. So everything, the temperature and pressure both increase. So what will happen in the high temperature? You will first form the first of all your metal will dissolve in water. Second, your metal form some complexes with the weak acids, and secondly, the metal hydroxides are formed. And by heating, you will form metal oxide. So I will show you. You can do it with different metal salts, but you should be careful. There is no fixed rule for synthesis of your material. You can synthesize different oxide material with different salts. You can dissolve it in different solutions. So there is no fixed rule. So if someone to synthesize wanted to synthesize zinc oxide, he can start from the zinc chloride, he can start from the zinc oxide, and he can also start from the zinc nitrate. It's depends. But what is very important is that you have to, Nasrin, after coffee. What you should consider is that for any person, you should work with your own tools and you should optimize your tools and you should get your own recipe. There is no concrete rule that 180 degree for 2 hours or 200 or this concentration or that concentration. So every laboratory, every person do it by its own self. Okay. The reaction chains happened in here was first of all the zinc from zinc acetate. Zinc acetate dissolved in water from zinc hydroxide, and then they add some weak base, and the Br is the base, and then the weak base will react with the Zn ion cation, and then by heating they transfer in the end to the zinc oxide and water. So the whole process is a chain reaction happening in a high temperature. The important thing is the additives you add. So if you do not add hydroxide, I'm sorry, if you do not add weak acid, you won't form, and you heat up the. If you do not add weak acid and you just add base, you will form zinc hydroxide powder. And if you heat up zinc hydroxide powder in water at a few hundred degree, it will form zinc oxide, but not the zinc oxide nanoparticle. It will form zinc oxide powder again. So we don't want the zinc oxide powder. We are looking for zinc oxide nanocrystal. So that's why we wanted to start from clusters and molecular large molecules and transfer large molecules to nanoparticles, not using the powders and transferring powders to another powder. That's a key point. Another thing I have to tell you is that your microstructure can change and can be manipulated by controlling your condition. If you control your condition, I mean the temperature, the salt, and the concentration of your acid and base, you can get the different nanostructures. But how we know that we get one nanostructure or we get another nanostructure? We should do experiments. If we don't do experiment, we cannot control it. In this example, some previous studies shows that people use zinc acetate as a salt with the CTB as a um, additive, acetic acid, weak acid. I think CTAB, CTAB is a weak acid. It's called citrimonium bromide. It's a weak acid I told you. If you don't use that weak acid, your ions will, your metallic ions will react with the hydroxide immediately, very fast. And when you have a fast reaction of your metal salts with your hydroxide, then you will result in powder. But in here, they use the CTB as a weak acid and NaOH as the base. Then they form hydroxide sol. Then the sol is transferred by heating in 2 hours. They get nanorod, the nano rods or nanowires of ZNO. And by 6 hours of heating, they get flakes, zinc oxide flakes. So the structure of resulting nanoparticle is very dependent on your synthesis condition. You may ask that what is the application of these zinc oxide nanostructures? Do you know some of the application of zinc oxide nanostructures? Anyone have any idea? Is there any advantages or disadvantage with the nanostructures? Any idea? What is the difference between zinc oxide alone and nanostructure of zinc oxide? The thing is that, can you hear me? Can you hear me?
Yes, doctor.
Yes, doctor, yes.
Yeah, if you have a bulk zinc oxide,
Yes, doctor.
yeah, the bulk zinc oxide is the large crystals of zinc oxide. So it's not have significant oxygen exchange with its surrounding. But if you have bulk zinc oxide, you won't have the significant oxygen exchange with the surrounding. I mean, the zinc oxide alone. But if you have the nano structure of zinc oxide, it's exchange oxygen with the atmosphere. So when it's lose oxygen, then you will have some zinc. You will have oxygen vacancies, okay, and the oxygen vacancies will increase the concentration of electron in your system. So, and when you have concentration of your electron in system, meaning that you will have increase in conductivity. Wow. So, do you have any idea what is the application of this? So, I changed the atmosphere, the oxygen concentration in the atmosphere. Then I will see that my zinc oxide nanoparticles can lose oxygen. So when it's lose oxygen, the concentration of electron increase. So when the concentration of electron is increasing my material, what it means? Do you have any idea what it means? Do you have any idea? The concentration of electrons means increasing the concentration of electron means you will lose, you will increase the conduction of your material. The carrier concentration of your material increase. So basically, you can build a pressure sensor, an oxygen sensor, with the zinc oxide nanomaterial. So zinc oxide nanomaterial is a very good option for fabrication of oxygen sensors. So these days there are many oxygen sensors working by changing the oxygen atmosphere or oxygen pressure in the system, and then your material will lose or even receive some oxygen from your atmosphere, and then its conductivity is increased or decreased. So based on the conduction of the zinc oxide nanostructure, you will have the control of oxygen in your atmosphere. So today there are many zinc oxide based oxygen sensors working. The other example is cobalt ferric oxide, or COF2O. So it's uh, it's composed of two cations. So one of them is uh, iron, and the other is cobalt. Both of them are dissolved as a nitrate in the water. Then we add sodium hydroxide. Then sodium hydroxide complexes is formed. Then we put it in autoclave, and then we heat it up 180 for 12 hours, and then we receive nano structure of copper iron oxide. What is the application of copper iron oxide? Do you have any idea what is the application of copper iron oxide? Sorry, cobalt iron oxide. Any idea, scientists? Copper iron oxide can be used as what? Do you have any idea? As a hard magnet. So it is a ferromagnetic material. So it can use as a memory. You can record voice or codes. And very simple thing is that you have it in your ID card, in your bank card. You have a magnetic strips or magnet bar in your bank card. So in your bank card there is a black strips. There is a code in that, which is basically is uh, your bank account and PIN code. And this magnetic strips is basically are powder of the magnetic material. Another nanoparticle can be iron oxide. Iron oxide is also synthesized by same route. First we start from salts, iron salts, chloride here, and then we add um, PEG 400 as a weak salt, as a weak acid, and then we add sodium hydroxide, and then we put it in the autoclave for 180 degrees C for how much hours? For how long? Let me take a look. For 16 hours, and then you will result in a dark powder. The dark powder is called, it's a magnetic nanoparticle, is Fe3O4. It's also you can use as a magnet bar or magnetic memory. There are many studies done that in 50s, 60s, but most of the studies in that time was based on the application of not nanoparticle particles. But here we have nanoparticles. We have nanoparticles. So if we form nanoparticles, we can use them as a magnet bar. So the examples are a lot. So we can use titanium salts. We can dissolve titanium salts. This is a Teflon liner. I told you. It's look like glass, but it's white. Teflon is a special polymer. It's expensive, but it is very resistant against the chemicals. So acid, base, high temperature. So that's why you use it. Then they use autoclave. Then they give it an acid wash, and in the end they have a white powder, which containing nanorods of titanium oxide. Okay, this is a nanorod of titanium oxide. There are many applications of titanium oxide. This is another application. This is another example for hydrothermal synthesis. They make a solution of your nanopar of niobium uh, and uh, and some water and some base. Then they add it to the liner, Teflon liner. They heat it up, and then they result in nanoparticles. And then they centrifuge it, and then they result in nano wires of niobium. Niobium can also contain sodium and potassium in their oxide, and they have the many applications. So I'm not going to details in here. So, any question? Question? Another
No,
oxide
Doctor.
can another oxide
So,
can be vanadium oxide.
no,
So
Doctor.
you can use the same route. So we start from the vanadium salt, then we uh, did the hydrothermal process, and here it adds some bases, and then it's form nanoparticles of particles of vanadium oxide, and then they decompose it, and then they form a nanostructure of nanopowder of vanadium oxide. Uh, all these steps, I mean, starting from salts to salt to uh, hydrothermal reaction and crystallization, all of them have the same route. Okay, you have the same route in this uh, process. You can change the cation. So if tomorrow you want to synthesize, I don't know, tungsten oxide or I don't know, very complicated oxide, you can do it. But the thing is that you should optimize your own process. So everyone try its own work. It's just like a cooking. There is no fixed process. So what you are doing here is studying and optimizing the process yourself. There is no one to to tell you what exactly the best temperature. You should find it yourself. So let's have a break. We will continue on the next session with